Congratulations are in order for one Georgia scientist who has broken his old record of measuring the longest lightning strike ever in recorded history. Joining me now to talk about that amazing feat, Dr. Michael Peterson, an applied physicist at the Georgia Tech Research Center, Severe Storms Research Center at the Georgia Tech Research Institute. Thank you so much for joining me today.
Yeah, thanks for having me.
So tell me, what is your new record and what date was that actually measured from?
Yeah, we actually found a new record for the largest horizontal lightning flash ever recorded. This one is now 829 kilometers from end to end, which is 515 miles. This is a flash that extended as a single flash between Dallas, Texas to Kansas City, Missouri. So it spanned multiple states, producing a lot of hazards for a large number of people.
For those who are not familiar, what makes a mega flash? What is it?
So when we usually experience lightning, we're usually looking at, for instance, a lightning flash striking the ground, maybe here in Georgia, looking out off from the distance and wondering about whether we're safe. Well, those flashes that we can see are not actually all that lightning is capable of producing. So generally speaking, if we're close enough to a lightning flash to be able to hear the thunder or see the flash, it's a good time to go inside. But some flashes, a very small percentage of them actually can travel over very large distances, not just the usual more or less 10 miles distances that we usually see lightning occurring from, but actually across hundreds of miles in this case. So generally when we look at lightning, we're usually talking about the convective hearts of thunderstorms, where you have the strong updrafts and other associated hazards like hail, tornadoes, etc. But actually the lightning flashes that occur outside of that convective core, the ones that occur kind of in the more peripheral clouds at the edge of the storm, those are the ones that are able to travel for long horizontal distances, essentially because of how the charge structures in those types of clouds set themselves up. They can act as conduits, allowing for lightning flashes to go a very long way from where the storm is occurring, well over the horizon, to strike targets that are very far away from where you might expect there to be a hazard.
And with it going so far in the horizontal, I'd imagine that increases the danger level even more because you're nowhere near the storm. Is that right?
Potentially, what it comes down to is you have to really be careful with understanding whether or not lightning can be a hazard. And a lot of it comes down to expectation. If you're under the severe thunderstorm warning, you are very well aware that you should be seeking shelter. But potentially, if you're out there looking to get back out in the lake, or if you're looking to go continue the rest of your day, you should take a second look to see whether or not you are truly safe to go back outdoors after the storm seems to have long passed.
And let me ask you, when you're measuring these very long lightning flashes, what tools are you using in your tool set? Are there certain satellite images that you're looking at, or how do you actually track these from space?
The nice thing is that our tool set is expanding every day. Back in the day, we only had ground-based measurements to look at least on a continuous basis. So the primary lightning sensor that used to be used was a lightning mapping array, or an LMA, and we actually operate one here at the SSRC. These are basically networks of radio receivers, similar to what you might have in your car, that look for static from lightning, and then they can use the coordinated times of those static impulses to be able to calculate where the source of the radio waves, the lightning flash, is actually occurring. But those old technology sensors, were still very useful, but they had a very limited range. You can only see maybe a few hundred kilometers, a couple hundred miles, more or less, around you. However, once they launched the new generation GOES satellites, NOAA's geostationary satellites, back in 2016, starting with the GOES-R satellite that became GOES 16, that actually was a game changer, because for the first time we could actually record the size of lightning flashes across basically the entire America's continent. Maybe not all the way up to the pole or anything, but at least the portions of it where lightning occurs. So we can see just how big the lightning flashes are, 24 hours a day, 365 days a year, and across the entire hemisphere. And that's what allowed us to essentially double the old records, going from the prior record from the LMAs of about 321 kilometers from end to end, all the way up now to 829 kilometers. So that was quite the quantum leap. But the thing is, this new flash was originally missed. And the reason for it is because, well, we have the new hardware, but it took a little time for the software software to catch up. It's a fire hose of data coming down from space. We can see basically every lightning flash across two different continents. That's going to be a hard problem computationally. And so, we developed some software that was able to find most of the mega flashes, but really we were able to finally be able to appreciate flashes of all sizes with a new approach that we employed in the past year that brought this old flash to light for the first time.
That is so cool how we get all this new technology each and every year. What was your reaction? I mean, when you finally measured it, you had the old record. What was it, over 700 kilometers? When you measured this one over 800, what went through your mind? What were you thinking?
I was honestly surprised. I didn't think that we actually missed anything from our initial assessments of those older flashes. And so to find a new lightning flash at the end of 2017, that was actually a bit shocking. This is the sort of thing that, it always tells you that, or shows you that it's good to do your due diligence, because just because you thought you were able to see everything the first time, there are always things that might be missed. So being able to double check your work is a very good thing for science.
So very surprising. And then what is the process like to certify that? It's not the Guinness Book of World Records. Where does that record hold? Who certifies the record?
Yeah, weather extremes like this are certified by the World Meteorological Organization, or WMO. When a new record is presented, then a committee of experts is convened to be able to discuss the record and assess whether or not it is valid and supported by available measurements. In this case, we actually took a decent amount of time before submitting to the WMO adjudication committees in order to make sure that we understood everything that was happening with the flash. So we looked at the geostationary data coming from the GLM sensor, NOAA's geostationary lighting imager. We also brought in the available ground network observations from the time. So we have the long range networks like the National Lightning Detection Network or Earth Network's Total Lightning Network. And then also portions of the flash were mapped by an LMA that's operated in Oklahoma. And so we were essentially able to bring together all these different measurements to make sure that what we were seeing was as we expected. And it turns out it was. And so that allowed us to start the adjudication process.
And how long before you try to make a four-peat? Doing it again?
Well, Mother Nature is always showing us new and interesting things. So with these new satellites that are continuously monitoring, looking at all the weather hazards around us, it's just a matter of time where if there's something new to see, we're going to eventually see it. It all depends on whether the data continues to flow and if it expands. Actually, one of the interesting and more recent advances in our field is that the Europeans are now launching, or have now launched, a lightning sensor similar to GLM that now covers all of Africa and most of Europe. Actually, it should be all of Europe, if I'm not mistaken. Anyhow, this new lightning imager, LI, on their Meteosat third generation satellite is going to be a game changer by allowing us to do everything we did with GLM, but now over 2 additional continents. So that's a larger swath of the Earth to look at in order to find these extreme cases of lightning.
And so more and more data coming in. Let me close with this. Why is it important, Dr. Peterson, to study lightning in so many different facets?
Lightning is a hazard on its own, but it's also very useful. So, the thing with lightning is that you never quite know if you're going to get struck. All it takes is one strike and you're out, like the famous quote goes. So even though you're not likely to get struck by standing out underneath a given thunderstorm, it's not worth the risk, because there's always a possibility that you will. And unfortunately, we see that happen, pretty often throughout the year, especially outside of the US. But the thing is that lightning is also a useful tool that allows us to peer inside what's going on within these severe thunderstorms, to understand how their updrafts are changing and how the charge and the precipitation is being redistributed throughout the clouds. So there's a lot of information we can glean by looking at lightning, which is a relatively simple measurement to make, just by providing this data set over a large part of the Earth. We can actually do a good job of understanding exactly what thunderstorms are doing and what they're capable of as well.
And a lot of lightning to be had this summer in North Georgia. Congratulations, Dr. Michael Peterson with the Severe Storms Research Center at GTRI. We really appreciate your time today. Congrats on breaking your old record.
Thank you. It's always a pleasure to talk.